Hey everyone, welcome back to my channel. Today we're going to be diving into the fascinating world of transformations in exponential functions. Transformations play a crucial role in understanding the behavior of exponential functions and can help us make predictions about their graphs. In this video, we'll explore the general form of transformations and apply them to a parent exponential function. And to make things even more exciting, we'll be using Desmos to visually demonstrate the effects of each parameter involved in these transformations. So sit back, relax, and let's get started. Let us begin with a short review of notation when talking about transformations. As always, we assume that y equals f of x is the parent function. That is, the function that we are starting with originally, the one that will be transformed into something else. You may remember from your early studies of transformations that the general form of a transformed function is as follows, just as you see over here. The transform function has the parameters a, k, c, and d. I want you to notice that I decided to use k for this parameter rather than b. In the past, we were using b. In general, it is customary to use b, but because we are using b for the base of the exponential function, I want to minimize confusions with variables. For this reason, I chose a different letter this time around. Now, what we're going to do here is the following. We are going to start with the parent function, f of x equals b to the x. And with this function as the parent function, I want to see what the general form looks. Whenever you apply all the transformations, A, K, C, and D, what will the general form look like? Remember that the general form that we just looked like had this particular expression, right? The expression A times the function f of k, x minus c, plus d. So to start, we're going to focus on this part right here. Let me actually circle that. I'm going to circle that in red. This is the part that we're going to focus on first. I'm going to go ahead and write it here. Right here, we have f of k, x minus c. And I want you to notice that what we have in this case is a composition. You can think of it as a composition where the inner expression, the expression k, x minus c, can be the inner function, right? In a composition, particularly in this case, we're only dealing with two functions. So the inner function is the expression k times x minus c. And then the outer function will be here the parent function, which is f of x equals b to the x. So if you remember how compositions work, the inner function is substituted into all of the x's of the original function. Now, the original function here only has one x. So this entire expression will be substituted into x right here. So what we are going to have is the following. Moving on here, what we are going to have is that f of k, x minus c, will be equal to b, but now instead of just having x, you are going to nicely have the expression k, x minus c. And that's what we have here. Now that we have this expression, in front of it, we have to place the coefficient a, and then at the very end, we place the term d, so plus d. So to finish it up, I'm going to write it like this. I'm going to say that g of x, the transform function, will be a times, now the composition, in this case b to the k x minus c plus the term d. And very nicely, this becomes the general form of the transformation when all of the transformations are applied, a, k, c, and d. Now in this case, we're going to talk about horizontal asymptotes, the parent function b to the x. No matter what b is, there's always a horizontal asymptote, and the horizontal asymptote is the x-axis. The equation of the x-axis is just the line y equals 0. But whenever we apply d, if you remember, is the vertical shift. Whenever we shift the graph vertically up or down, we're also shifting the horizontal asymptote. So the new horizontal asymptote becomes exactly the value of d. So as the equation, it will be y equals d right here. So if d is 3, then that means that the new horizontal asymptote is the line y equals 3. If d is negative 5, then the new horizontal asymptote becomes the line y equals negative 5. Now here, what we are going to do is we're going to go and see exactly what happens whenever we apply the transformations like a, k, c, and d. I want you to notice the effect of every single transformation. Now, because this is not the first time that you're studying transformations, I think that you can already kind of see what the effects of these parameters are, but it never hurts to review. I want to review with you exactly the effects of A, the effect of K, the effect of C, and D on the original function, on the parent function. What happens when we apply A? What happens when we apply K? And so forth. We're going to go ahead and look at this demonstration by using Desmos. Here I have the basic function, exponential function 3 to the x. I chose b to be 3, no particular reason. And I want us to see exactly what's going to be the effect on this graph if we play around with the parameters a, k, c, and d. We're going to start with a. Now, from your earlier studies of transformations, you may remember that a affects the function in two possible ways. If a is negative, the function is reflected about the x-axis. But if the magnitude of a, so for the magnitude, I'm going to use absolute value. Absolute value removes the noise of the negative sign and focuses on the magnitude. So if the absolute value of a is bigger than 1 or between 0 and 1, then there will be a vertical stretch or a vertical compression. Right now, let's focus on the sign. What happens if a is negative? And for the sake of simplicity, I'm going to make a -1. Right now here, if you don't see a negative, notice how you just see 3 to the x. That means that a is +1. And this is exactly the graph. All of the other graphs that we're going to generate will be compared to this red graph. The red graph is the basic parent function. So if a is -1, what really happens in this case? See what happens here by turning a negative. Look at the blue graph over here. The blue graph is the reflection of the red one right there. So you really notice that if a turns negative, there is a reflection about the x-axis. I'm going to go ahead now and remove that out. Okay. So now for the sake of simplicity, I'm going to remove the negative. Now we know that if there is a negative involved, that just means the reflection. I'm going to play around with magnitude. Let's say that we make the magnitude of a, so the absolute value of a, let's just make it a number bigger than 1. Let's say 2. So Again, I'm not going to use -2. We already know that the negative will do a reflection. I don't need the negative. I'm going to focus on now just the magnitude. So here A is 2. So I'm going to put a 2 here and multiplication. So 2 times 3 to the x. Notice what happened to the blue graph right here. The blue graph is now narrower. If it's narrower, that means closer to the y-axis on the right. See how it's a little bit closer than the red one. There you can see nicely the vertical stretch, and the vertical stretch by a factor of 2. Now what happens if I now change the 2 to a number between 0 and 1. So let's keep it simple and choose 0.5. If you look now at the graph, look at the blue graph. Now the blue went below the red graph. This is now signaling a vertical compression. It was brought down, boom, vertically down. So now it's below the base function, is below the red one. And that means that there is a vertical compression by a factor of 0.5. So again, I'm hoping that this is nothing new to you. Okay, so I will remove now this one. I don't need it. Now we're going to focus on the red graph, the base graph, versus the green. The green will be the transform. Let's now look at the effect of k. If you remember right here on the left, this is k. Now k also affects the function in 2 ways, if you remember. If k is negative, you will now have a reflection about the y-axis. And then we're going to look at the magnitude of k. That means the absolute value of k. That will affect the graph by performing a horizontal compression or a horizontal stretch. And you'll see exactly how that works. So I'm going to use the green graph for that demonstration. I'm going to go to the exponent, you see there. And right now I just have 3 to the x. That means that k is positive 1. So what I'm going to do, and notice how the green graph is matching perfectly with the red, because I haven't done any transformations yet. But now I'm going to change that. I'm going to make k -1. So I'm going to say negative here. And see how nicely the red graph was reflected about the y-axis beautifully. That's what the negative does all the time. It causes a reflection about the y-axis. So now I'm going to remove the negative. Now, hopefully we are convinced about having a negative k, and I'm going to now keep it positive. I want to focus on the magnitude, the absolute value. So let's make k be a number bigger than 1. Let's make it 2 again. And notice that in this particular case, let's look at the green graph. When k is a number that is bigger than 1, notice how again you got a horizontal compression. The graph has been compressed horizontally. It is closer to the y-axis when a number is bigger than 1. Now, what happens if, oh, and by the way, if you remember, the compression is by a factor of 1 over the absolute value of k. It's always the reciprocal of what k is equal to. Again, if I'm going fast through this, it's because I am assuming at this point that you are familiar with the basic effects of transformations. So now I'm going to use 0.5. And if you notice, by making k equal to 0.5, let's look at the green graph. The green graph now, it's wider. It has expanded horizontally. So we have a horizontal expansion in this particular case by a factor of 1 over the absolute value of k. In this case, k is 0.5, 1 over 0.5. Now I'm going to remove this graph right here because we're going to focus on the other transformations. So now we're going to be looking at the red graph versus a purple graph. So what we're going to do now is to look at the effect of C. And you may remember that C signals a horizontal translation, either to the right or to the left. So I'm going to keep everything else positive. I'm going to keep a positive 1, k positive 1, because now I want to focus on the effect of c. I want to see exactly what c is doing. I'm going to have to enter here brackets. So x minus, and let's say that c is positive. Here, the magnitude is irrelevant. Whether c is between 0 and 1 or bigger than 1, that's irrelevant. When it comes to c, it's all about the sign, whether it's positive or negative. So if c is positive, let's say something like 2, I want you to notice, actually, you know what? Let me even make it more dramatic. Let's say 5. Look at this. I want you to notice how the entire graph was shifted to the right by 5 units. Look at this point right here, the y-intercept. It was at x equals 0. And now this point has shifted over to the right by 5 units. So a horizontal shift to the right. Now, what happens if I make c negative? If I make c negative, if c is negative 5, this negative that was there originally will become positive because you're going to have a negative times a negative. So this will now be positive. So positive 5, let's keep it at 5, and see now what happens. Now all of a sudden, the red graph was shifted to the left by 5 units. Follow what used to be the y-intercept here. It was at 0, 1. Now it has shifted to negative 5, 1. So you see that shift nicely. So that's the effect of c. We'll remove this graph. And now I am going to focus on this one right here. Now it's going to be the red graph versus the black graph. So what we're going to do now is to focus on D. I'm going to keep everything else as if it's not there. And I'm just going to focus on the effect of D. So in this case, again, I don't care about the magnitude of D, whether it's a number bigger than 1 or between 0 and 1. I only care about the sign, if it's positive versus negative. So what happens if it is positive? Let's say positive 3. Notice how we now have a vertical shift up, and we have it by 3 units. Again, we're going to follow the y-intercept. It was at 1, and now it goes 1, 2, 3 units upwards. And that also means that we have shifted the vertical asymptote. In fact, I'm going to go ahead and include the equation of the vertical asymptote. That's going to be 3. Let me change the color of that so that we keep it different. I'm going to make it orange. So notice in this particular case now that we can nicely see the horizontal asymptote right there. So now what happens if D is negative? So if D is negative, let's say something like -3, notice now how we have a vertical shift downward. So this y-intercept is shifted 1, 2, 3 by 3 units. And in fact, the new horizontal asymptote will be y equals, and then here is going to be -3. So is this blue horizontal line that you see right here. Well, that's a wrap for today's video. I hope that you found this exploration of transformations in exponential functions informative and interesting. Remember, transformations are a powerful tool in understanding and predicting the behavior of exponential functions. If you have any questions or comments, feel free to leave them down below in the comment section. And don't forget to like and subscribe for more math-related content. Thanks for watching, and I'll see you in the next one. Bye for now, everyone.